Hello everyone, welcome back to the latest lecture session. In the first couple of classes, we've been looking at, or I was trying to give you some background about wastewater treatment and why it's necessary. And we also looked at prejudices and such and the role of class. But we are not going to obviously go into that aspect here. Let's move on and see where we are. In the last class or the session, we were looking at groundwater quality report from a village near Roorkee, and surprising aspect was in one of the samples, or in both the samples, pardon me, we had or we came across coliform. Total coliform was not nil, but it was for this case I guess it was at 40, or it's 40 per 100 ml, and it was 1600 for the other one, right. And I believe we looked at the case, or I provided the information where I mentioned that the 1600 one was drawn relatively closer to the surface, and the one that gave the result of 40 per 100 ml was relatively farther from the surface, and I mentioned the role of leaking septic tanks, right. So, coliform, again before I go further, why coliform? Why not different other indicators? One, it's because it's present in greater numbers in our intestines or the gut. Coliform is present in the gut of what is it now? Warm blooded animals, let us say. Here we are talking about humans, so I am just talking about me or us here, right. So, firstly it is present in great numbers, and even after I discharge it, or if it comes out through the feces, right, it is going to be able to survive, others maybe not. So, we need an indicator organism that can survive, can be relatively easily measured, and also is present in relatively greater numbers. So, that is why people choose coliform. Again, total coliform is an indication of how can I put it here in layman's terms, indication of contamination of your relevant water sample by feces, let us say, right. So, that is something to keep in mind, and obviously that can lead to different kinds of diseases, and we looked at the mortality rates and such and so on. We will not go into that in detail now, and in that context, to give you an idea about the what do we say, situation or scenario of Yamuna, we talked about, or we presented this particular aspect or set of data from 2018 in the winter months. So, we see that it is pretty poor, or the concentration of the or we see that fecal coliform count is remarkably high. MPN here stands for most probable number per 100 ml. We will look at the test and the details later, but again the point I want to make is Yamuna more or less is partially treated or untreated sewage, at least downstream of Delhi until Mathura, Agra and even Etawah, let us say, right. So, why is that important? Again, you are going to have contamination of the soil obviously, because it is not just untreated sewage, it is also industrial wastewater coming in, and you have what is it now, people living on the banks depend on the water for either agriculture, daily usage or such, and the water from Yamuna goes to Mathura and Agra and certainly Etawah too, right. So, though they treat the plant, I mean treat the water, pardon me, we still have to be relatively careful about these aspects, right. Otherwise, we are going to end up what do we say, causing a pandemic or such, or leading to the transmission of disease among a lot of people, transmission of pathogens, pardon me, right. So, that is one aspect why we need to look at water and wastewater treatment, both go hand in hand. Why is that? As you know, I am going to use the water, right, and then after I use it, it becomes wastewater. The issue in India is that we are not treating a lot of this. I will get the data later when we talk about the wastewater. So, this is going back and diluting or being diluted by surface water bodies, or is more or less polluting the surface water bodies, and again we are ending up using the relevant water, and that leads to diseases and so on and so forth. So, wastewater and water both go hand in hand, that is something to keep in mind. Earlier they just used to what do we say, dump it downstream of the city, but with industrialization now we are having to, let us say, water, and this is wastewater, we now have to be able to what do we say, treat it first, right, treatment, and then send it to dilution in surface water body and then water treatment plant and then our usage, let us say, right. But the scenario slowly but surely is coming out to, let us say, surface water body, right, surface water body. I am going to have to discharge it into a river. After dilution, then the water treatment plant is going to treat the water and then we are going to use it. After usage again it becomes wastewater and so on. But now the scenario is so dire because of increasing population density and overdrawn groundwater. The scenario is dire, at least in South Africa and some other places in Africa and some places in Europe too. So, treated wastewater or the wastewater is treated to such an extent that it is directly sent for usage by the local population. Usage might not be for drinking, but certainly for what do we say, toilet flushing and so on and so forth. In the future we are going to be at the, I am relatively sure, no, I am sure that in the future we are going to be at the stage where the treated wastewater is going to be used for almost all human needs now. So, that is something to keep in mind, right. Let us move on here. So, we were talking about pathogenic microorganisms or pathogens. So, we will look at this in greater detail later, but the aspects or the microorganisms that we obviously need to be concerned about, I have, I guess, highlighted them, right. So, we will come back to this bacteria, archaea and eukarya, right. So, we will come back to this later, but that is something I wanted to mention here. Do I have the sizes here? So, sizes, I am concerned about bacteria, viruses, as you can see just RNA, that is why the size is remarkably less, protozoa, some kinds of worms, right. And the aspect here is that filter sand is 100 to 1000 micrometers and it can strain and remove particles up to the size of 30 micrometers and or even 20 sometimes. So, obviously, I can't remove the viruses, right, not all certainly, but protozoa and sometimes we can even get some bacteria though, right. So, that is something to keep in mind and here is just the relevant profile. Note the size out here, it is micrometers, right. So, what book is it that you can look at or what are the references that you can consider? So, obviously, Water and Wastewater Engineering Design Principles and Practice, first edition, I think even the second edition or the Indian edition is certainly available by McGraw-Hill and it is Davis and Mackenzie, right. The other one thus is again a relatively more comprehensive source, certainly used for practitioners and also for faculty. Wastewater Engineering Treatment, Disposal and Reuse, but now I guess instead of the third edition even the fourth and the fifth editions are out, let us say, right, again by Metcalf and Eddy, let us say, McGraw-Hill publishers. Again different other sources, this is another good source with respect to unit operations and process, let us say, by Reynolds. In general, this book is more or less good enough for the UG students, let us say, right, that is something to keep in mind. Before we go further, let us look at the course outline, right, to understand what it is that we are going to discuss throughout this particular course, right. So, introduction, we will have a look at some of the, we already had a look at the history, we will briefly look at the different kinds of treatment plants only briefly and very generic discussion about the design process required. And then before we start getting into wastewater treatment or such, we are going to review the fundamentals. Obviously, people might not have the background in the relevant aspects as in concentration, flows or mass balances. So, we will have to look at that, or those people who do have a background might be relatively rusty in these areas. So, we will have a look at that, right, and then we will look at mass balances. Mass balance as in let us say you have your wastewater treatment plant, inlet, right, influent is coming in and outlet is going out. You have to design it, right, you have to know what chemicals, not what chemicals, yes, in a bit about it, yes, but how much of it to add, let us say, what flows, let us say, what concentration, when to add and such. So, those aspects we will obviously look at it when we talk about mass balances, right. And then we are going to move on to discussing wastewater treatment. Other people typically look at water treatment, but I find wastewater treatment relatively more interesting. So, we will talk about wastewater treatment initially or first and then move on to water treatment. wastewater, right. So, head works as in, you have wastewater coming in, people dump all kinds of stuff. So, you need to remove the grit, you need to remove the plastic and other bigger screens. So, that is why bigger particles and such that can mess up your mechanical instruments. So, that is why you have bar racks and screens, grit removal, let us say the bigger particles and such. And then you are going to have sedimentation, as in, let us say if I add some sand or soil, let us say in a glass of water, after some time I can see that some of it will or you can visualize, not visualize, you can see some settling right then and there. Or if I come back after, let us say 2 hours or 3 hours, I can see more of it having settled out and only some being dissolved or still suspended out there, right. So, how do I remove these particles? Obviously, by sedimentation, gravity, or you are going to help it settle by letting flocks being formed, let us say, right. So, that is one aspect. And then biological treatment. So, after I remove this suspended matter or suspended what do we say, particles from your wastewater, I still have some suspended matter and also some dissolved matter, and here it is organic content, right. Think of your urine, your feces and the kitchen waste, I mean the water, here we are talking about the water from your washing utensils, washing your clothes and so on and so forth. All this is coming out here and you need to be able to treat it. But how are we going to do that though? If I try to treat it chemically, that typically leads to higher costs. But similar to us, the bacteria also need energy, they want to thrive. So, using that principle, people have been able to develop different kinds of biological treatment, yes. And the principle there is that the bacteria are going to use oxygen as the electron acceptor. I am also taking in oxygen as the electron acceptor, that is the same reason I am taking in oxygen here, right. And similarly, aerobic microorganisms or bacteria are going to take in oxygen as the electron acceptor. They are going to use our waste as their food, which people also call as substrate, right. And then the relevant redox reaction, you are going to have the energy being used by the bacteria, let us say, or they are also going to use it for this reaction, they are going to use it for cell synthesis too and reproduction, let us say, right. Maybe reproduction is not the right way, right word, growth, let us say, right. Again, same case here, I eat food, I take oxygen, I use the energy, and some of the waste I am going to discharge it, and that waste is the food for the microbes. So, again different aspects, we will discuss that in greater detail out here. So, nutrient removal also, that is what we have here. Nitrogen and phosphorus is also going to be released from different sources, not just from our urine, let us say, and you have to remove it. If not, this nitrogen and phosphorus will end up in surface water bodies. I believe I have a good figure or picture which people find pretty funny. We will look at that later. And if not, if you do not remove these nitrogen and phosphorus, what is going to happen? These nutrients, you are going to have algal growth, and when you have excess in a short period, you will have an algal bloom, let us say. And once this nutrients inflow is shut down, what is going to happen? You are going to have death of this algae, let us say, and then you are going to have considerable issues with decay of these algae. So, again dissolved oxygen in your water and such is going to come down, you are going to have fish kills and such, let us say, and also some of the algal blooms are pretty toxic. And then you are going to have secondary settling and such. And disinfection, we know that we need to remove or not remove, pardon me, take care of the different pathogens in this wastewater, and that is why we have disinfection. Once we are done with wastewater, we will move on to water treatment. So, preliminary treatment, first sedimentation, as in let just gravity do its job. If not, then we are going to have coagulation and then flocculation, right. Coagulation, you are going to neutralize the charge on the suspended particles, let them come together and form flocks. Once they form bigger particles, they will be able to settle down, right. So, that is the principle out here. Flocculation, once they form the flocks, they will settle down, you have sedimentation. And those that are too small to settle down even after coagulation and flocculation, or those which will take too much time, you are going to remove by filtration. Sand filtration is one typical way to get that done. And then disinfection by chlorine or HOCl, and the issues with such disinfectants, I guess that is something you are going to look at. So, softening, because even if you remember, we looked at the data from the village near Roorkee and we saw that the hardness was pretty high. So, other than leading to issues with your digestive system, it will typically lead to issues whenever you are trying to wash something, because it is going to use up or form a complex, if I may say so, with your soap, let us say, right. So, that is one reason why you are going to have to remove your calcium and magnesium or decrease the hardness. So, lime soda softening, and then ion exchange. People have moved on from what is it, typical carbonation and recarbonation relevant aspects for lime soda softening. If there are other cations or anions that I want to remove, you are going to have different resins which can absorb your not adsorb here, I guess here the principle is ion exchange. So, you are going to have calcium what do we say absorbed by the resin instead of the sodium and such, let us see. So, ion exchange softening, then filtration, desalination. Yes, we have huge desalination plants near Chennai, I think 200 or 100 MLD plants, and then residual management, we will look at what residue is and such, I guess, right. So, general overview, we are going to look at material balance to understand, let us say, how do I analyze these systems. For example, I want to design it. Design meaning, first let us say I want to know the size or the volume that is required of my either the water or the wastewater treatment plant. So, how do I do that now? I need to then be able to understand how much is coming in and at what level can I send it out, and then how is it being transformed within my particular reactor or treatment plant. And then using the principles of material balance or mass balance, we will be able to get it done, right. So, then after that we will look at wastewater treatment and then water treatment. So, let us go back to our own slides out here. So, before I go further, we will just look at this particular wastewater treatment plant that we have here. So, this is the one from IIT Roorkee. So, you see this sump, wastewater will come into this sump. We will look at this video in much more greater detail later, but for now we will just look at an overview to get your interest, what do we say, to capture your interest, let us say, okay. So, here we have our what is this now, the sump out here. This is where the sludge is managed, but we will look at that. Typically it comes into the wastewater is coming in. How does wastewater come to this sewage treatment plant? Typically by gravity, right, because if you have it upstream, not upstream, up the slope, it is not going to work out. You have to have pumping stations and then again costs. So, you have a sewerage network which collects the sewage, and the sewage comes to the sewage treatment plant. And in and in India, the issue is that our sewage collection system is so poor or non-existent in some cases, but again this is expected, we are a developing country, right. It either leaks or there is no sewerage network, or the sewerage network is so poor or poorly designed that these sewerage pipes are blocked, because you need to have a particular velocity, otherwise they are going to settle, right. There are multiple issues. The reason I mention is that we have plants here, let us say I am not going to mention the location, 250 MLD. 1 MLD, MLD is million liters per day. 1 MLD 1.5 crores or so, it takes 1.5 crores or costs 1.5 crores to construct a plant of 1 MLD, but again it is not linear though. So, 250 MLD, let us say 300 or let us say 350 crores, let us say, right. And the issue is that they are only receiving 40 MLD or such. Why is that? Because the sewerage network is so poor, the sewage is either leaking in, or there is no network, or the flow is not going through in the that they in the way that they wanted it to happen. So, wastewater, it is going to come in and then it is going to be pumped up, right, and then you are going to have what do we say, some equalization tank, we will look at that later. And then here let us say we have the basins here or the tanks here, reactors here, where the sewage is being degraded by microbes. The bubbles that you see here are the air or oxygen, or is the air or oxygen that is being pumped into this particular system. You can see that out here, right. During this process the microbes are degrading the relevant sewage, and after I stop aeration, let us say, so you see the flocks These are different kinds of, okay, now you can see the flocks more clearly, right. Let me see if I can get a better shot somewhere out here, okay. And these being heavier will also settle down. So, I guess you can see them already starting to settle down. Let us see if I have a better picture. I think I have it collected in a beaker, and so the supernatant. So, once the bacteria, while the bacteria are feeding, you have different kinds of bacteria being formed, and you want balance between floc and filamentous, and you have this floc forming bacteria, and right now they are suspended in the water. So, when you let them settle, they are going to settle down to the bottom, and all the top water which is being collected out here, that is what you see out here, is the supernatant, and that is relatively clear, and that is the treated wastewater more or less, right. So, that is something that you see. Decanting, let me see if I have the picture. So, this is the sample that we are going to look at right now. The sample we are going to look at right now is from the aeration tank, or the microbes just spent, let us say, a couple of hours degrading the waste in there, and now the person took, or we took the sample from there, and we just put it out there to help you visualize how the floc, again this is bacteria, let us say, right, are going to settle down, right. This is now real time, I am not fast forwarding it or such. You can see the time out here, right. It is already starting to settle and such, and given enough time you will see considerable settling. It is just a matter of seconds here with respect to settling of most of the what do we say, sludge here. This is what I am going to call as sludge, and this is my supernatant, which is relatively clear. After some time this is also going to settle down, right. So, that is something that you can visualize or see out here, right. So, in I guess 30 seconds is what we looked at here or spent out here, and we see that it is pretty relatively fast. Again, that is because these flocks now are relatively heavier, and now you see the floc, not floc, pardon me, the supernatant, which is relatively clear and treated water. So, here for just an experiment, I guess, or in different angle, right. So, you can see this too. Okay, so then this sludge, what are you going to do out here? You have to dewater it and treat it. If not, you are going to have an issue. We will look at what I am trying to do out here. So, here you have the dewatering equipment and such. Otherwise, the volume of this sludge and the weight is going to be high. So, you want to remove the water. So, that is why they are adding a polyultralight, right, to form flocks, and we can see this sludge coming in. Sludge that is collected from the bottom. You have a filter press out here, and the sludge, dewatered sludge, as you see, is falling down from out here, right. Yes, this is the dewatered sludge that is composted typically. So, that is enough for now. We will look at this greater, not greater, in greater detail later on. So, let us come back to where we were. We looked at the references and such. So, coming back to our course out here, right, water and wastewater, as I mentioned, are interlinked. A few of the slides or the data which I could not find, let us say, I sourced them from the MIT Open courseware. The link is out here. You can search for it in Google, and this is the course here, let us see. So, whenever I am typically providing the source of the information or the slide that I am taking. If not, obviously we will draw it ourselves, let us see. So, this is for the US. Obviously, I could not get the actual one for India, but it will be relatively similar. So, here we have water, and here we have on the y axis water use and wastewater flow in gallons per day. Gallon is around 3.7 liters, 3.7 liters per day, right, per service and such. Leave that aside. So, time of the day, but this is way back in 1961, but our water usage now should be relatively similar, if not way off. So, you see people start waking up, getting ready for their offices and work. That is why a spike in what is this water usage, right. So, and then slowly but surely again most of the people are at work, or it is only kitchen waste that comes in, or wastewater from the kitchens. And then in the evening again when people come back, you see, and bathing and such, you see that increase again, or the spike, and then the decrease again. And if you look at what we have, the relevant wastewater, you will see that it matches similar profiles. So, typically I think we take it again when we are designing for a city or such, we assume that 85% of the water that we are giving to the population will end up as wastewater in our wastewater treatment plant. So, that is something for you to keep in mind or understand. And typical domestic water use, right, to understand what is it that people typically use it for. Note that again this data is from the US, I could not get specific data for the Indian scenario, but it is relatively similar, but this is for the middle class and such, let us say, and upper middle class, let us say. The reason I say so is, as you can see, toilet flushing takes up a considerable chunk of the water, and now efforts are on to see to it that we decrease this water that we use for flushing the toilets, let us say. So, that is one aspect, that is why Indian style toilets, obviously that is the reason why they take up less water. Toilet flushing, as you see, takes up a considerable chunk, the majority of the water is used for toilet flushing. And as I mentioned earlier, some of the treated wastewater is planned to be used for toilet flushing, and you see the reason here why, right. So, then obviously bathing, right, and laundry and kitchen and other usages, I guess, including drinking probably is pretty less. Again, bathing, laundry for washing clothes and kitchen. So, this is the breakdown out here, right, that is for understanding what it is that we are using the water for. And again here I have another set of data, hourly variations in flow, as in, for example, in the morning when I flush the toilet waste, let us say, or the human feces and such, the flow might not be a lot, but the concentration of the organic content, let us say, is going to be high. But when I am bathing it, the flow might be high, but the concentration of the organic content in that flow will be less, right. So, we just need to understand that, because again similar to people, bacteria too can't take shock loads. Let us say I have started exercising and I am able to lift only 5 kgs or such, let us say. I can't jump from a 5 kg squat to, let us say, 70 kg squat in one go, right. So, you want to prevent shock loading. So, that is the reason why you typically need to understand the flow rate, concentration and mass loading. That is why you have something called a equalization tank at the beginning of your wastewater treatment plant. You want to equalize the mass that is going to come in contact with your various unit process, let us say. So, what do we have? We have two aspects here, concentration here and flow rate, and the product will be the BOD mass loading. BOD mass loading is kilograms per hour, and concentration, I guess they are using different units, grams per meter cube. Flow rate is meter cube per second. So, as expected, initially flow rate is going to be high and it is going to decrease, and in the night it is going to be relatively low, that is what we see, and again it is going to go up. So, cyclical. So, same profile, but relatively lesser here during the morning, I guess, because bathing and such and cooking take place around this time. But with respect to the mass loading, I guess again similar profiles, but you see that the concentration here is going to be obviously not concentration, the units are different. The mass loading is nothing but flow into the concentration. You can look at the units more or less, let us say, right. So, what do we have out here? The mass loading too follows a similar profile. So, how do you capture this and equalize this particular mass of the organics that is coming into your wastewater treatment plant is always an issue, and that is why we need to design our equalization tank well, right. Let us move on. So, typical wastewater treatment plant, this is what we have. Before we understand the wastewater treatment plant, let us see what it is that we have. But I think I am almost out of time. I do not want to leave this in the middle. So, thanking you for your patience, I will end today's session.